Hey, this is Kenneth, and today I'm going to be talking to you about a brief introduction to code division multiple access. Code division multiple access is a modulation scheme that allows multiple stations to share a single channel. So, for example, if we look in the frequency domain, so this is frequency, and this is power, a traditional station looks like this. In a traditional multi-user RF system, you would then have a separate channel here, a separate channel here. So for example, when you look at something like Citizens band radio, you have 40 channels that are numbered sequentially, and each one is a separate frequency that is far enough apart from each other that they don't interfere. This of course becomes problematic because it means that you have to allocate to every station a specific frequency. So if we have 3 stations here, and they're trying to talk to 3 other stations over here, each one of these needs to be assigned a separate number. This works fairly well when you're looking at such systems as public safety, since each county and each jurisdiction has a very fixed geographical area. But when you start looking at something like cell phones or other multiple station systems, the number of channels you would need grows beyond any reasonable number, and the ability to try and allocate fixed channels for each one would become prohibitive. With Cdma, instead of you using the difference in frequency as what lets you get multiple stations on the air, you use what's called multiple codes. So again, looking at these 3 stations, if they all used the same frequency, normally the 3 receiving stations wouldn't be able to tell any of them apart, and it would sound like just noise. But with Cdma, what you do is on this single frequency, you have each station encode their signal in a different coding or chirp set that allows the receiving stations to take the single signal that is received and separate it into the 3 distinct stations in this example. Looking at the block diagram for a transmitter, you would have your data coming in, you would have a modulator, so this is your LO, and so at this point you would have your whatever your modulation would be it binary phase shift keying at at your band frequency. You then mix it with this set of chips that is one of the multiple unique codes to the channel before it goes out to an antenna. As long as each of these chipsets or codes for each different station are different on the receivers, if they synchronize with the chipset or codes of the station they're interested in, they can receive it and exclude all of the other ones. So now we're going to talk about how you actually generate and synchronize these chips. So the only criteria for the code, all the codes that you use to multiplex on a channel, is that they are orthogonal in some domain. What this means in the binary domain here is that however long they are, as it's going to be a string of 1s and 0s, that each one of them is numerically unique from the others enough that you can tell them apart. For example, if we had a 8-bit long code, there's 256 possible codes between all 0s and all 1s. Of course, all 256 of these codes are not really good codes for Cdma because the orthogonality between all 0s and all 0s except for one of them is terrible. Right? All 0s put you... So if this is our center frequency, and then we were using the Cdma to binary phase shift coding, 0 would always shift you on the lower phase, and all 1s would always put you on the higher phase, but this one would put you here 7/8 of the time, and then here only 1/8 of the time. This doesn't get you very good isolation between this one and this one because you can only differentiate them 1/8 of the time. This system is used quite a bit in cell phones, but one of my favorite applications for CDMA is actually the GPS system. Global Positioning System. GPS is based on the fact that on planet Earth, here we have some green here. And blue. So here's planet Earth. It's a pretty sweet Earth. Around it, there are currently 31 satellites orbiting on a number of inclined planes. Each of these satellites transmits on a small number of frequencies the exact time of this satellite. Some station on the ground then receives the signal from each of these different satellites, this one and this one for example, and then uses the difference in time of arrival and the speed of light to calculate exactly where that station is. This is something that's useful that people are used to thinking about on a linear domain by if you are in one place and you can get a direction on some unknown station, and you're in another place and you can get another direction on an unknown station, you can get a pretty good idea of where that station is. GPS takes what is relatively simple in the two-dimensional domain and extends it to the four-dimensional domain of latitude, longitude, altitude, and what time it is. This is important since we can't tell you the angle in GPS. We can only tell you how much farther away one station is than another. The problem is the GPS system needs to all be on a very fixed set of frequencies so that receivers can be tuned for those single frequencies. The specification for GPS allocates 5 different frequencies, but the only one that's of interest to most people is the channel that transmits coarse codes, which is on 1.57542 gigahertz. This is a single frequency that all 31 satellites transmit on. So if this is a satellite, and this is another satellite, and this is another satellite, each satellite has an antenna tuned to specifically 1.57542 gigahertz, as does every single one of the receivers. So over here we have a device like your cell phone. Cool. And so each of these 3 signals come in to your cell phone on the same frequency. Problem is, your cell phone needs to be able to differentiate between each of the signals to be able to take them apart, get the information out of each satellite, and then use it to figure out where they are. In coarse adjustment, this is done using a single millisecond repeating code. So each satellite modulates their information at the information they're broadcasting at 50 bits per second, which is unbelievably slow. And the information they send is what time it is, what the calendar day is, what the status of the entire GPS constellation is, and where all of the satellites are. This information is sent at relatively low speed since it's not a particularly complex amount of data. And so even at only 50 bits per second, it can go through it in only a few minutes. And that's the differentiation between a cold start versus a warm start versus a hot start on a GPS receiver, which is another long story. But the main thing that we're interested in is how do you tell each of these apart? And that's done using a 1023-bit code that each one of them mixes with their inputs so that your cell phone then has to sit there, and there's only 31 different codes. All right, so let's see. So there's 31 satellites, and each one of them has a 1023-bit sequence that they rotate through. Since the channel, the chip rate on GPS is 1.023 megachips per second, this 1023-bit sequence repeats once per millisecond. Which means that if your receiver, so if we have the whole GPS system here, which is modulating useful information, and then it goes into a mixer with this sequence. So it's just a bit of 1023, it's a string of 1023 ones and zeros that's clocked at 1.023 megachips per second. So every millisecond, the sequence here repeats and spreads what is normally a narrowband signal a little bit wider. Alright, so at that point it goes up to the antenna, and then we go through space here, and then we go to the receiving antenna on the station, goes through a down mixer to the whole GPS receiver. Right here, we need to feed in the exact same sequence from here at the correct phase after it goes through the air like this to de-spread what is a narrowband signal here, and here becomes a wideband signal, back into a narrowband signal. This is, since there's only 31 satellites, the receiver has to pick one of the satellites and then try and lock onto the sequence of that satellite. So it has the GPS receiver has saved from the last time that it successfully got an almanac from a GPS satellite, the list of 31 1023-bit sequences that are currently in use in the constellation. The receiver would then pick one of those sequences and try and line it up somewhere in the received data stream and see if it correlates strongly with any of the received signals. If it does, it's found one of them and it has locked onto it. If it doesn't, it shifts it all over by one bit and tries again. Then when it wants to, if it catches it, it catches it. If it doesn't, it has to shift it over again. So it tries this 1023 different times for each satellite to try and get a lock on it. This is the part that a GPS receiver is talking about when it says that it is a 5-channel or a 10-channel or a 20-channel GPS receiver. Because it doesn't make any sense to talk about channels when you only have one frequency. If it's one frequency, channel in the traditional consideration doesn't make any sense. But if the receiver can sit there and try 20 simultaneous chip sequences, it has a much better chance of locking onto GPS satellites faster, and that's what makes higher channel GPS receivers better. It's because they have more code channels, not frequency channels. So, to review Cdma and list off a few of the other big advantages of it, Cdma is really good at allowing multiple access to a single frequency. That isn't the only one. There's also the fact that it prevents jamming and interference. When you're transmitting a narrowband signal, like you normally do, so for example, a basic voice channel is 15 kilohertz wide. A cell phone conversation is on the order of 1.5 megahertz wide to 20 megahertz wide. If someone else comes in and either deliberately or accidentally puts another large carrier on that same frequency, it obliterates your signal. But if you take that and through Cdma, spread it so that the power is spread over a large spectrum, this intentional or unintentional jamming interference only obliterates this small fraction of the power. When you then convert it back to the narrowband section at the receiver, so this would be the receive signal, you don't convert any of that power. You only convert the one small fraction of the power that happens to line up with the code that you're using. And so the interfering signal appears very, very much weaker. So this was me talking about code division multiple access and how it allows multiple stations to use a single frequency, and the fact that since you're spreading the code, you're spreading your power across a wider domain based on something other than frequency, it allows you to be much more robust against both jamming and interference, and it also helps prevent undesired listening, since you can use this spreading as a part of a encryption system to make it appear like what is an actual useful signal is just noise. So thanks for watching.